Okay, so we might as well get started. Um, so last time we had talked about, we had finished discussing transport phenomena, and now we're going to start discussing the Reynolds transport theorem and apply it to deriving the governing equations of combustion. Then after we do that, then we can start getting into applications, because you guys will start seeing how all this stuff comes together once we start getting into propellant combustion and multi-phase combustion. Okay, and so what we had finished up on Friday was just refreshing your memory on some basic tensor stuff like a dyadic product, things like that. So for those of you who've been in fluids one or convective heat transfer, even if these weren't defined, you have definitely seen these before. So basically none of this should be completely new. There's double dot products, various identities. I prefer vector notation for my governing equations just because they work in all coordinate systems, even though they are a bit more cumbersome to write everything. So, and just we'll be using, when we derive the equations, because in your grad classes, you've probably seen Navier-Stokes derived about 20,000 times. So I'm not going to go, so I'm going to derive them the fast way. I'm not going to go through the infinitesimal control volume approach. I'm going to use the Gauss divergence theorem approach. Okay, and so just to refresh you what that is the volume integral of the divergence of a vector is equal to the surface integral of that vector dot n hat, and integrate that over the surface. And then there's a similar one for a pressure gradient term. Okay, and then now for the governing equations, we're going to start from what's, if you recall, is the Reynolds transport theorem, where that just states that the time rate change of the amount of extensive quantity B in your system is, and would be the form where you follow this would be the form that you would use for how the conservation laws themselves are traditionally written. Like say Newton's second law, F equals ma, or F equals dp dt, where p is the time rate, where p is the vector of momentum. Those are written to be following a particle in space. And if you recall, this RTT is the link where you can basically write a conservation law like this and take it from a Lagrangian frame of reference and then transition it to an Eulerian frame of reference, which is over here. Okay, and so that's basically all this is. And in your fluids classes and things like that, you've probably seen different forms for different things. I'm writing one particular form where we include the motion of the surface itself, because our control volume, the boundaries may be expanding or shrinking with time, or the control volume itself may be moving through space. Okay, and so we need to account for those. And for those of you, like I said, most of the time VB is 0, but if you work with engines, like IC engines, where you have the piston moving up and down, your control volumes will basically squash and expand as the piston moves up and down. And so there are some codes that are there's some computational fluid dynamics codes that take that stuff into account. Okay, and so you guys should have definitely seen this before, probably pounded into you in your fluid mechanics classes. And then one thing that I will derive is the material derivative. This is sometimes called the substantial derivative. It's sometimes called the Lagrangian derivative, because it is the differential form of this operator right here. But anyways, so that will be given by cat d, cat dt, and that's given by the time rate change of a variable psi plus the velocity vector dotted with the gradient of psi. And so that's all that will mean. Okay, so you guys, most of you should have seen this, if not all of you. So now we'll apply it to deriving the governing equations. So with conservation of mass, we have the very fundamental conservation law for conservation of mass is that the time rate change of mass of your system is equal to 0, which means if I'm following a blob through space and this thing is moving around, conservation of mass basically states that that the mass of this blob as it's moving through space is constant. Okay. So and then the mass is just the volume integral of density in our control volume, which I'll define to be here, which this implies that B that we use in our Reynolds transport theorem is simply 1. Okay, and so then we use the RTT and apply it to the time rate change of mass with B equal to 1, and that gives us the time rate change of mass in the control volume plus the net mass flux of material moving out through the control volume. Okay, and so if you are working with a control volume form, you stop here. Like all the CFD engines codes, those work with a CFD technique called finite volume, and they actually stop here and then solve these equations here. Other codes, like the ones we use, we actually solve them in differential form, so we need to derive the governing equation itself. So what we do then is we assume, if we're going to derive the differential forms, we assume that the control volume is stationary and non-deforming. So if it's non-deforming, we can actually move the time derivative safely inside of the volume integral. If it's deforming, you can't do that. And if it's stationary, then the velocity of the boundary is also equal to 0. Okay. So then we have the volume integral of the time rate change of density plus the surface integral of rho v dot n hat dA, then that quantity is equal to 0. And we can use the Gauss divergence theorem because we have a vector rho v dotted with n hat, and we are integrating that over the surface area. So we can use the Gauss divergence theorem and turn this into a volume integral, and this is equal to the divergence of the vector. The vector is rho v, so this is equal to the volume integral of the divergence of rho v, which is the mass flux. Okay. So then if you do that, we have a volume integral here. Oops. We have a volume integral here and a volume integral here. We can combine them. And we have this quantity here. We have the volume integral. Oops, get rid of this dv. We have the volume integral of the time rate change of density plus the divergence of the mass flux over the volume is equal to 0. Okay, and so this has to equal to 0, and we're free to choose any control volume we want, except for a control volume that has 0 volume, because that makes no sense. So the only way to make this true for any generic control volume is if the integrand itself is equal to 0. So if the integrand itself is equal to 0, this statement here is always true regardless of what the control volume is. Okay, and so we can conclude that that conservation of mass in differential form is the time rate change of density plus the divergence of the mass flux, and that's equal to 0. Okay, and so this is something that I suspect most, if not all of you, have seen before. So it's really, for the most part, just review. And you may have derived it with an infinitesimal control volume, which I'm not going to do because it takes forever. Where you have a control volume of width delta x and height delta y, and if the instructor is really mean, he or she will do it in 3D too. And so there you just apply the RTT on all of the edges and use a Taylor series expansion, and in the end you wind up with the same thing. Okay. Now, this here's conservation of mass. It's the one that, for those of us who work with compressible flows, like my group, or Scott Stewart's group, or basically any other, or and Bala's group, we all work with this equation here directly. We don't play any games with it. And that's because we have to deal with shock waves and other discontinuities in the flow. So, however, in a lot of other applications, you can assume that this this rho v is differentiable. So if you have a shock wave, we'll call this rho v, and it's initially 0. So you have if you have a shock wave moving into air, like from a blast or something like that, you'll have some sort of rho v profile that will look like this. So a common trick that's done in most of your fluid mechanics classes and heat transfer is that you would apply the vector version or the divergence version of the product rule on this term here. And so you would, so you would use that product rule, and you would expand that into v dot grad rho plus rho times the divergence of the velocity. Okay, and then what those classes would traditionally do is they would recognize, like they would then recognize that this term here, if I go back up to my material derivative definition, this here is just my material derivative with psi replaced with rho. So this term down here is nothing more than d rho dt. Okay, and then you would basically say that the that d rho dt is equal to minus rho times the divergence of the velocity vector. Now, for smooth flows or low Mach number flows or incompressible flows, this always holds. However, if there's a shock wave, you cannot do this because if you have a shock wave, there is a discontinuity in the quantity rho v. Okay, so if there's a discontinuity in the quantity rho v at the shock wave, or the discontinuity, it is non differentiable. So if it's non-differentiable, if rho v is discontinuous, grad rho v is not equal to, or not grad rho v, the divergence of rho v is not equal to v dot grad rho plus rho times the divergence of the velocity. Okay, and the reason that you can't do that is because this quantity here is non-differentiable. It's like when you're learning the product rule in Calc 1 way back in the day, that they said you could use the product rule if the function was differentiable. And you in Calc 1, you guys probably, and I certainly didn't, we never dealt with functions that were discontinuous. So it was something the instructor said, and a minute later you basically pretended that never existed, or that caveat to the product rule never existed. Well, for those of us who work with blasts and shock waves and things like that, we live in that caveat. So if you start seeing substantial derivatives, that's usually a sign that the equations are written for a low speed flow that does not have shock waves. And basically what I mean by smooth flow is that all of these quantities here are smooth and differentiable. Okay. So are there any questions on that?
Now, couldn't you just treat your shock wave as not being discontinuous, though, if you were looking at a time frame that was short enough?
In like physically, yes, you are correct, and that's just because a shock wave is actually continuous, but its length scale, but you would need to get onto the shock length scales. And so the physical length scale of a shock is about, I think it's on the order of 2 to 3 mean free paths. So you would need to so your control volume size would need to get down to ones to tens of nanometers. So it's just more of a practical issue than it is anything. But there are people who have actually done DNS simulations of the viscous structure across a shock wave. But they're just so thin that for any practical calculation, so if you plot rho v for this moving shock wave in free space, it would look something like this. But this distance here would be on the order of, I don't know, at most 10 nanometers. Okay, I mean for normal applications, and if your control volume is this small, the continuum approximation that is inherent to this conservation of mass derivation. In fact, it's the only assumption that we made here, is that our material is a continuum. If our control volumes are so small that we start resolving the structure of the shockwave itself, we are actually violating our continuum approximation. An application where you see very thick shocks would be an atmospheric reentry, and that's just because, again, the thickness of the shock is a couple of mean free paths, but it's just that in the upper atmosphere, the density is so low, there's just a giant amount of spacing between all the molecules, and so in there, and so in the upper atmosphere, if you have a supersonic or even hypersonic flow, you have like shocks that are physically thick, but that's just due to the very low density of the environment that they're in. Okay, but they use completely different models to simulate that, because the gas is so rarefied that this equation here is no longer valid. But we are not going to discuss that. That is a very specialized field of the people who have to deal with that. Okay, are there? But that was a good question. Typically, when I bring up this differential point to undergrads, I get a bit of fighting. Okay, so we did conservation of mass, and we basically wrote it in a form that you traditionally see for that is used for basically low speed flows. Now, one thing I will, I'll mention this later on. Okay, so species mass. So here we have that the mass of species I is just the integral of the volume integral of the density times the mass fraction of species I. And so if we're to apply the RTT to this, you would find that small b is just equal to yi. Now, there is one thing, there are a few things that we do need to consider here. So we have v, is that A, we can have chemical reactions, and those chemical reactions can be changing can be basically adding or removing a species from within the control volume itself. So we need to account for that. And we can have mass diffusing out through the surface of the boundary. So I'm just going to call this m dot I double prime diff, because as we just discussed in transport theory, there are all kinds of models for that. So I'm just going to label them as m dot I double prime, and I will switch to the diffusion velocity form basically later on. And this omega dot I is the mass rate of production. Okay, and it's just and it's given by the molecular weight of species I times the time rate change of concentration of species I due to a chemical reaction. So this here would come from the law of mass action. Okay, and so and so the net and so if we're going to apply the RTT, which is really just a control volume analysis of our goofy kidney-shaped control volume. I don't know why when they do the RTT version of the governing equations, all of the control volumes are kidney, or they're either kidney bean or they are potato shaped. They're just always that way, including mine. Anyways, so we can find that the total mass rate of production, because it's occurring within the volume, is just the volume integral of the mass rate of production. So that would give you the total rate of mass of, say, O2 that is being depleted within this control volume. Okay. And then the net diffusion mass flux out is we have this m dot double prime, or this diffusion mass flux going through the surface. And so if you want to find the total amount of mass diffusing through the surface, you need to integrate it over the surface. Okay, and so to integrate it over the surface first, we only care about the stuff that's going through the surface. And so we dot it with, and so we take this diffusion mass flux vector, and we dot it with n hat to get just the component that is going through the surface. We do not care about the portion of mass that may be diffusing along the surface, because our RTT says nothing about what's happening tangential to the surface. It only states what's happening across the surface. Okay, and so the net diffusion mass flux out, and I will emphasize that it's leaving the surface. And that is just the surface integral of m dot double prime, or the diffusion mass flux dotted with n hat dA, like I just said. And we can replace our diffusion mass flux with basically rho yi times the diffusion velocity for species I. Okay, and so taking these two things into consideration, our conservation law for species mass would be the time rate change of species mass is equal to the production of species mass for species I due to chemical reaction minus the net loss of species I mass due to diffusion through the surface. Okay, and so now our RTT is not equal to 0. It is equal to these two additional terms. And these would be a similar scenario where you had an RTT that was not equal to 0 would be conservation of momentum, where you have a right-hand side. And so species mass is the same way. So again, we use the RTT. We're going to assume a stationary control volume. So we have the time rate change of species mass inside the control volume is equal to the net mass of species I moving through the surface due to bulk flow. And so basically this this rho yiv is just the mass of species I that is being carried through the surface. Okay, and so if we have net flow going through the surface like we do here, there is species mass that is also being carried with the fluid. Okay, and this term here, and these two terms here directly came from the RTT, and now I need to set it equal to the right-hand side, and so we gotta account for the diffusion mass flux out, and the chemical reactions. Okay, so now you could imagine. First, we're using a non-deforming control volume, so I can take the time derivative and move that in. So I have the volume integral of the time rate change of species mass. And I'm going to use the Gauss divergence theorem here. And again, assume a stationary control volume. So the boundary velocity is 0. And so I use the Gauss divergence theorem on this term here, and I get the volume integral of the divergence of rho yiv, and that's just the species mass flux. And I'm going to apply the divergence theorem to the diffusion mass flux term. And so if I do that, I just take this v dot n hat and I replace it with a divergence. And I do nothing with the chemical reaction term. Okay, and so now all four of these terms are now volume integrals. And I'm gonna, since basically these two terms here have a common rho yi, I'm gonna take this and move it into a common term here. And so if I do that, I wind up with the volume integral of this expression here, of that. And then again, we have to play the same game. Is that to make this true, I could actually, if you feel more comfortable with this, I could subtract this and make this equal to 0, same difference. So I could play the same game to make this always true. Is that the statement in the integrand must always be true, and so that means that this that basically this equation here is always equal to 0, or the integrand is equal to 0 to make it true, just like we did for conservation of mass. And so if we do that, our differential form of the species mass equations is partial rho yi partial t plus the divergence of the species mass flux plus the diffusion mass flux, and that is equal to the net rate of production of species I due to chemical reaction. And so this term here physically represents the accumulation of species mass inside of the control volume, and this term here represents the represents the net flow of species mass out due to bulk flow and mass diffusion through the boundary of the control volume. Okay, and so this here is the species mass equation, and then you can prove that the sum of all the species mass equations equals the conservation of mass. So in other words, if I have n species and I take all of these equations here and sum them up, you will wind up with conservation of mass, a normal conservation of mass, and that's basically because A, you've accounted for all of the mass, but B, by definition, the sum of the mass fractions has to be 1. And by definition, the sum of conservation of mass demands that the sum of yi vi is equal to 0. And conservation of mass also demands that the sum of omega dot I, oops, not prime, is also equal to 0. And that's a consequence of, again, conservation of mass. Basically, this states that this states that chemical reactions cannot create or destroy mass. Okay, and so if you were to sum up all of these species mass equations and apply these properties, you would in fact wind up with you would in fact wind up with conservation of mass. So so that leaves a question then. If you have n species, and if you add up all the species mass equations, you have an extra equation. You have conservation of mass, and you have, say, if you have 10 species, you have 10 species mass equations. So, in other words, you have an extra equation because at least one of them is linearly dependent. So then, what do you do? How do you account for this? There are various ways of doing that. But in our code, what we do is we just solve all n species mass equations. And if we solve the species mass equations for all of the species, you will implicitly recover conservation of mass. And we have verified that we implicitly recover conservation of mass. The other way to do it is you solve conservation of mass and the species mass equations here for all but one species. And then the mass fraction of the last species is computed using yn, I'll call that n, is equal to 1 minus the sum of I to n minus 1 yi. Okay, and so that's just another way of basically doing this. Is you don't solve the species mass for the very last species, but you get its mass fraction from the definition of mass fraction. Okay, and there are pros and cons to each approach in practice, but both are equivalent. Okay, and from a strict mathematical point of view, they are both identical approaches. But if you're doing a CFD code, there are sort of computer science and numerical issues, basically slight differences in pros and cons. If this was a course in numerical combustion, I would definitely go into those in a lot more detail. But I'll just mention in passing those two different ways of basically dealing with the extra equation. Okay. So again, we're going to play the game that if the flow is smooth, because again, if you look in most books, you will find this equation here in passing. But for those of us who work with compressible flows, we have to work with species mass equation in this form right here. We can't do any really fun games with it. So if the flow is smooth, we can use the product rule on rho yi and basically break that into yi times d rho dt plus rho times dy dt. And we can use the divergence version of the product rule. And so I'm going to break it up so that a vector that the vector is rho v, and the scalar here is yi. So I have rho v dot grad yi plus yi times the divergence of the total mass flux of rho v. And I'm not going to do anything special with the diffusion velocity. Okay, and so here I just used the divergence version of the product rule on these terms here. Okay, so I can collect terms here. I have yi times d rho dt plus yi times the divergence of rho v. I can collect those two terms together, and if you notice here, these two terms here, these here are just the total conservation of mass. So I can, which is equal to 0, I can cross those out. And then I have the density times dy, or partial yi partial t, plus v dot grad yi. And that there is just the material derivative of yi with respect to time. And then plus I got the diffusion velocity, and I got the chemical reaction term here. So putting it together, the form that you will typically see in books would be this form of conservation of mass, where you have rho times dyi dt plus the divergence of the diffusion mass flux is equal to the mass rate of production due to chemical reaction. So are there any questions with this?
Professor, can you go over the difference between earlier when you had VI and just regular V?
Oh, VI, this here is the diffusion velocity. So let me scroll down. So V is the fluid velocity.
Okay.
And VI is the diffusion velocity.
Okay.
And say for Fick's law, where we had the diffusion mass flux was equal to equals minus rho d B is equal to minus rho d grad yi, right? You remember that, right?
Yes.
And this is also defined to be equal to rho yi vi. Okay, and then this quantity here was called the diffusion velocity. And then if you want, you can solve, you can equate these two and solve for the diffusion velocity, assuming Fick's law, which is not always accurate. Okay, but it equals to minus d over yi grad yi. Again, that's for Fick's law. Okay, and because there are lots and lots and lots of models for the diffusion velocity, we tend to just write it as cap vi and basically leave it like that. We do not substitute in that the diffusion mass flux is equal to this directly, just because then your equations would only be valid for, say, Fick's law, which is used for theoretical purposes, but computational for predictive calculations, we use one of the more complex versions that I discussed last week. Okay, and so that's the difference between the two. And also, if you notice why we write it like this instead of a generic diffusion mass flux term is because if you look at the species mass equation, it's right here, is that at least in this form here, which is called conservative form, at least this term here, the diffusion diffusion mass flux velocity is just basically added to the bulk flow velocity. Okay, and so you could think of it as due to mass diffusion, the absolute velocity of species I is actually moving just a tiny bit faster than the bulk flow, and then that's due to the mass diffusion. Okay, and so, and it also makes the equations compact, and this expression here is also valid for any diffusion model that I want to use. I just need a way to actually compute the diffusion velocity. Okay, and then you guys will be using a code called Cantera. And the reason I went into all of the mixture averaged and Stefan Maxwell / multi-component formulations was because in Cantera and Fluent and things like that, and in CFD codes, you have the option of choosing one or the other. And so, and so basically I'm going over what these are because when you make modeling choices, you will have the choice of which model to use. And so, but are there any other questions? Okay, now momentum. I'm not going to go over that. You guys have seen this about 100 million times, starting from your undergrad in fluid mechanics. So I'm just going to skip straight to the result for that, where we have the accumulation of momentum is equal to the net momentum flux out plus the pressure forces, and that's equal to the divergence of the viscous stress tensor, which is given right here. And I just write it in its full general form, plus any body forces. Okay, and so you guys have seen this before. I'm not going to go into any more than that. If you've taken Fluids 1 or Fluids 2, you guys have dealt with this a lot. Okay, and again, if the smoothest flow, or if the smoothest flow, if the flow is smooth, you can do the same trick with the product rule, and you wind up with this, which again is the more common form. You see it written in books, but in our CFD codes, we actually solve it in this form here because it is strictly conservative, and you need that property to maintain good shocks and things like that. Okay, and energy. Again, you guys probably went over this derivation several times, so for a reacting flow, it is no different, surprisingly enough. So you have the time rate change of energy in the system is equal to the net heat in plus the net work in. I like defining all my energies to go into the control volume instead of having the heat going in and the work going out, which is traditionally done in engineering thermodynamics. And this ESIS is just the volume integral of the total energy, and the total energy is small e, the internal energy. This includes chemical, and sensible, and the departure energy. Okay, and plus the kinetic energy. And since we deal with gases and things like that, we almost always neglect the actual potential energy. Okay, and Q dot in, if you remember from your heat transfer, that's just minus the Q dot n hat dA, because you have your control volume, and you have n hat, and you have your Q vector going in. Okay, and so, and that's fighting n hat, and so that's why there's this minus sign here. And again, we can apply the divergence theorem to this term, and we get minus the volume integral of the divergence of the heat flux vector. And again, the heat flux vector for a reacting flow is much more complex than the one you guys dealt with in heat transfer, because in addition to the heat conduction term, we have heat transfer due to species mass diffusion, and also a heat flux due to the Dufour effect, which is normally neglected, but not always. And work dot in is just the velocity dotted with the force vector. And if you recall from your fluids, that you had forces acting on the surface of the control volume and within the control volume. And if you basically do that, I'm going to skip this because again, you guys have all seen this before several times. But if you skip that, the work dot in would just be minus the flow work, which is basically which is just P times V. And also you have a work due to viscous stress acting on the surface of the control volume. Okay, and so now Now, one thing, and so now we are now ready for conservation of energy. Let me ask a question. Do we need to account for energy due to chemical reaction?
And you say you included that in your internal energy term?
We included the enthalpy of formation in the internal energy. So in this form, if we include this term here, are we going to have an extra energy source term due to chemical reaction, or a heating term, if you will, due to chemical reactions occurring inside of our control volume? Are we going to have one or not?
No, you wouldn't have one then.
No, you would not have one, because that is accounted for in the enthalpy of formation term right here. And so, and that's one of the beauties of including the enthalpy of formation in your total energy definition, is that your energy your is that your energy equation is in the end no different. It is the same energy equation that you have dealt with. Again, I'm going to skip all the steps. You guys have seen these before, or at least most of you have seen them before. And you just rearrange and play some games, and your total energy equation here is the same one that is the same one that that you may have that you certainly derived in fluid mechanics, and you may have derived in say gas dynamics. But the only term here that may be new is that you got the divergence of v dot v dotted with the viscous stress tensor. Again, this is a legal tensor operation, and if you want to learn, like, going into the details of tensors is way too much for this class. But if you want to learn more about those, fluids one would be is a great place to learn that stuff. Okay. And so note that this term here is actually nothing more than the total enthalpy. So it's just the internal energy plus the kinetic energy plus P over rho. I can group the E plus P over rho, and this here is just the definition of enthalpy regardless of the equation of state. Okay, and so it's just H plus 1/2 of V squared, and that's just equal to HT or H tot. It depends on what terminology that you guys are used to. And then again, I note that E is equal to the sensible energy, actually plus EAG. Oh, yeah. It's equal to the energy, the internal energy departure function, plus the ideal gas energy, which is the sum of all the species mass fractions multiplied by their enthalpy of formation, plus the integral of CV dt. Okay. Then if the flow is smooth, you can play the exact same game. And basically, you just take this term, you take the total energy terms here, and you replace them with rho times their the material derivative of that term here. Okay. And so this here would be the total energy equation in non-conservative form. And the heat flux vector here, again, you would use the same long one, so that's minus lambda grad T plus Q interdiffusion plus Q Q4. And this interdiffusion flux is equal to the sum of all the species of rho, yi, vi, hi. Okay, and so this is what Q equals. Okay, and so really the only difference between this and a normal compressible fluid flow is the addition of these two terms here. Okay, and also I will note in deriving these equations here, we have made no assumptions on the material. We made the only place we made an assumption and stated explicitly that the material is a fluid is in conservation of momentum, right here. This here is the only part where we have assumed that the material is a fluid. If we just say it's a generic stress, and that stress can come from solid mechanics, these equations are valid for solids and fluids and plasmas. They are valid for any material. The only assumption inherent to these is, with the exception of this term right here, is that the continuum approximation is valid. And so Scott Stewart has a postdoc working on compressible solid mechanics. I have a student working on that. And so we basically solve these same equations here, but it's for solid mechanics rather than fluid flow. And the reason we solve the solid mechanics in this type of form here is because it makes it a lot easier to couple to a gas dynamic flow. And so, but the total energy equation is the same. Everything is the same. So we've made no assumptions on the material itself. Okay, and I'm out of time. And so what I will do on Wednesday is basically work with the various forms of the energy equation, because you normally in books you often don't see it written in a total energy form, but you'll see it written in either a temperature form or an enthalpy form. So we'll go through and basically briefly go through those, and then we will discuss boundary conditions at material interfaces, like at the surface of a metal particle. How do you handle changes in quantities across that interface? And then after we do that, we will be ready to start discussing propellant combustion. Okay, any questions?